Hi, I'm Brandy Heflin. I'm a personalized physics instructor, and I help high school and college students feel confident and successful in learning physics. Welcome to week 2 of my AP Physics exam preparation video series. This week, we're taking a look at questions that test multiple topics within the same question. Sometimes those topics fit together seamlessly, and sometimes they seem a little contrived, as you'll see when we go through this week's questions. The questions students can expect to see on the AP Physics 2 exam include 1 on experimental design, 1 on qualitative to quantitative translation, 1 paragraph length response or paragraph argument, and 1 short answer. The question in this video is type number 2, qualitative to quantitative translation. We'll be taking a look at AP Physics 2 2019 question number 4, which tested geometric optics, fluids, and the ideal gas law. A student notices many air bubbles rising through the water in a large fish tank at an aquarium. In the figure below, the circle represents one such air bubble and 2 incoming rays of light, A and B, are shown. Ray B points toward the center of the circle. On the diagram, draw the paths of rays A and B as they go through the bubble and back into the water. Your diagram should show clearly what happens to the rays at each interface. So here's the diagram reproduced, so we've got a little bit more space to work with. So the fact that ray B is pointing at the center of the circle is very important, because if you recall from Snell's law, that a ray that is aligned with the normal isn't going to be refracted at all. And a line that passes through the center of the circle is already along the direction of the normal. So ray B is going to pass straight through the air bubble undeflected. And I find it helpful for figuring out what's going to happen with ray A to sketch the normal at each interface. So here would be the normal for the point where A first intersects the air bubble. And since we're passing from a material with a higher index of refraction to one with a lower index of refraction, our ray is going to bend away from the normal line. Now we're going to want another normal line at that interface. And because we're passing from a material with a lower index of refraction to one with a higher index of refraction, our ray is going to bend toward the normal as it exits back into the water. And so here is how this was scored. We're going to get 1 point for ray B passing straight through. We are going to get 1 point for ray A bending away from the normal. When it passes into the air from the water. So that's going to be this point right here. And then for this refraction point here, we're going to get 1 more point for ray A bending the opposite direction in relation to the normal. And let me explain what that means. So, and this is as it exits, let me be clear, as it exits air back into water. So what this means is if you got confused and accidentally drew ray A getting closer to the normal on the way into the air bubble, but then bending back away from the normal on the way out, you would at least get partial credit here for recognizing that ray A is going to do the opposite thing at the second interface as what it did at the first. And again, that awarding of partial credit is something that the scorers do try to be reasonably generous about. And this follows along with the idea of only penalizing you for the first mistake and then not penalizing subsequent uses of the thing that was maybe a little bit wrong as you have to take that information into subsequent parts of the question. All right, and in part B, the bubble has a volume V1, the air inside it has a density rho A, and the water around it has a density rho W. The bubble starts at rest and has a speed Vf when it has risen a height h. Assume that the change in the bubble's volume is negligible. Derive an expression for the mechanical energy dissipated by drag forces as the bubble rises this distance. Express your answer in terms of the given quantities and fundamental constants as appropriate. So this one seems like a little bit of a fun challenge, right? Let me grab this. So we're going to think about our bubble displacing from here to here, where it's going to have, I should have written a velocity of 0 here, and here it's going to have a velocity of v final. So it's going to, travel upward, and this is going to be over our height, h. And actually, I want to really just make that a more accurate, physics diagram there. We don't need an arrow that represents velocity or changes in position in between, really. So how do we know what to do here? Well, we're talking about energy dissipated by drag forces. So we've got to be talking about some kind of relationship between forces and energy, and the bubble is rising this distance. So that says to me, work energy theorem. So that's in fact what we're going to start with, that our net work done on the bubble will be equal to the change in its kinetic energy. So we need to think about what forces are acting on the bubble. We are going to have a buoyant force. We are going to have a gravitational force, and we're going to have some kind of drag force. And I haven't necessarily drawn these to scale. In fact, I would want to really actually make that buoyant force bigger by quite a bit, because obviously the bubble's accelerating upward. Okay, so that means we're going to have an expression for the work done by the buoyant force minus the work done by the gravitational force minus the work done by the drag forces. Let's go ahead and call it F or W drag. I should have labeled it drag on the force diagram as well. That will be equal to the change in the bubble's kinetic energy. Okay, so now we're going to need an expression for the work done. Where do I want to write this? Yeah, we'll just write it here. So we need an expression for the work done by the buoyant force, and that's going to be equal to well, the buoyant force is going to be equal to the density of the fluid multiplied by the displaced volume. So we can write this as rho W times V1, which was the volume of the bubble, times GH, because of course the bubble is displacing a volume V1 of fluid of density rho W. Now let's talk about the work done by the gravitational force. We're going to need, again, we usually think about mgh. Well, how much is the mass of this air bubble? It's going to be the density of the air, again, times volume V1 that the air bubble takes up, times GH. And so now we're ready to make some substitutions with rho W V1 GH in place of the work done by the buoyant force, minus rho A V1 GH for the work done by the gravitational force, and then the work done by the drag force is what we're going to find. And that's going to be equal to the change in kinetic energy, which is a half mv squared. But again, that mass is going to be the density of the air bubble times its volume, so just rho A V1 times V final squared minus 0 because the bubble started off at rest. So now we just need to rearrange for the drag force, or sorry, the work done by the drag force, and that will be equal to rho W V1 GH minus rho A V1 GH minus 1/2 rho A V1 V final squared, should be volume 1 times V final squared. So here are our scoring points. We're going to get +1 for a valid application of the work energy theorem. We are going to get +1 for a correct expression for the work done by the buoyant force. And then our final point is going to come from correct substitution into an equation with consistent relative signs for the terms. So that's just a matter of being careful about thinking about which of these forces would be giving the bubble the energy to rise and which ones would be taking it away. And part C. At a particular instant, one bubble is 4.5 meters below the water's surface. The surface of the water is at sea level, and the density of the water is 1,000 kilograms per cubic meter. Part 1. Determine the absolute pressure in the bubble at this location. So this is pointing to, of course, finding the pressure at a depth within a fluid. So that pressure is going to be equal to the atmospheric pressure plus the density of the fluid times G times H, where we usually use H to mean the depth in the fluid. So for this question, we know that that's going to be the density of the water times G times D for this depth that we're at. Because we already used H for something different, so we don't want to repeat variables here. So this is actually a pretty straightforward calculation. Our atmospheric pressure is 1 times 10 to the 5th pascals, plus our density of the water, 1,000. You can use 9.8 or 10 for G, and then times D of 4.5, and we're going to get a pressure of 1.44 times 10 to the 5th pascals, or you'll get 1.45 times 10 to the 5th pascals using G equals 10 meters per second squared. And so the scoring here is really simple. You get 1 point for correct answer with units. And part 2. The bubble has a volume V1 when it is 4.5 meters below the water surface. Assume that the temperature of the air in the bubble remains constant as it rises. In terms of V1, calculate the volume of the bubble when it is just below the surface of the water. So this is talking about 2 different volumes at 2 different pressures. That's ideal gas law. So we can say P, which is the pressure we just found, times V1, which is at the depth of 4.5 meters, equals our atmospheric pressure times the volume at the surface. So again, how do we know this? Because we've got volume V1, we've got a depth, we've got at the surface, and then in terms of V1, we're going to calculate volume. So, all right, so we just now need to solve for the surface, which will be that pressure we just found times V1 divided by atmospheric pressure. And we're going to have 1.44 times 10 to the 5th times V1 divided by 1 times 10 to the 5th, and we're going to get 1.44 V1, or again, you might get 1.45 V1 if you used 10 meters per second squared for G. So how was the scoring? Oh, I lost my cursor. Happens at least once every video. So we're going to get 1 point for applying the ideal gas law. And then our second point is going to be for substituting a pressure consistent with part C1. And part 3. If the air in the bubble cooled as it rose, the volume of the bubble would be less than the value calculated in part C2. Oops, that should be C2, not C3. Use physics principles to briefly explain why. Okay, so the last part was talking about changes in pressures and volumes. Now we're throwing in temperature. Definitely ideal gas law. So we are going to need that pressure at 4.5 meters times V1 divided by, we'll just call it T1 at 4.5 meters. And then that will be equal to the pressure, atmospheric pressure, times the volume at the surface. Divided by our temperature at the surface. So let's solve for volume at the surface, where we're going to have our pressure at depth times the V1 times the temperature at the surface, all divided by our atmospheric pressure times T1. Sorry, I started to write the wrong thing. Times T1. So the pressures would be the same. As in part 2. But this part is telling us that T1 is greater than the temperature at the surface. So that means that our volume at the surface is going to be smaller because we now have this extra factor, T surface divided by T1, which is less than 1. So we'll be able to say, so the surface will be smaller. I almost forgot our scoring. Oh my goodness. I was so ready to move on to the end. So, and this one is very simple. This one is just going to be +1 for a correct explanation. So I hope you have enjoyed this explanation of a Physics 2 question that handles multiple topics in the same problem. If you have a request for my YouTube channel, you can send it to physicsproblemrequests@gmail.com, but I'm not going to be putting those up until after my AP exam series is done. If you need some assistance via email, you can reach me at freephysicshelpline@gmail.com. If you want to know more about my online physics tutoring services, you can email me at brandyhaflinphysics@gmail.com. You can visit my website at virtualphysicsofficehours.com, or you can find me on Facebook. I'm Physics Tutor Brandy. Just a few notes and disclaimers. AP is a registered trademark of the College Board. The College Board does not endorse or recognize this video or my services. All of the materials presented are available on AP Central at the link shown here for the AP Physics 2 exam. And those materials include the release-free response questions, the scoring guidelines, and sample student responses and commentary. I strongly encourage students to review those sample responses to get a feel for the different level and quality of the responses prepared by the students who took these release exams live, and to see what the scores for that year were looking for and how they decided to award points. If you have any questions, you can email me at brandyhaflinphysics@gmail.com. I'm Physics Tutor Brandy. I love physics, and I love helping you. Until next time.